Can we read the ingredients label?
It's on the little packets.
Oh.
They're not organic, but oh my God, I forgot my notes. I'm gonna have to run and get them.
Can't pull?
Thank goodness you feel every single day. Like, actually, he runs around Johnson Field. Yeah. He's super dedicated to the ground. Yeah. Let me write down the first 200 digits. What are the first 200 digits of J0?
Yeah, the J0.
Okay. Camera's still on? Okay, well, what are you going to do? First of all, are there any questions? All right, then. Let me go over a few more things about Dirac fields and component representation. Let me in particular mention something about the Majorana mass term. One way of writing it is minus a half m C transpose sigma 2 C plus C dagger sigma 2 C star. Now, if you write that out, what you see is this is minus 1/2 m, and this thing here is C1 to C2. Why I chose C, I don't know. It's one of the hardest letters to write in any alphabet. And so this term in particular is minus a half m, C1 to C2, and this one is minus I C2, I C1, and then plus the other term. And so altogether, if you put them together and pull out the I, what you see is that this is C1 to C2 minus C2 C1 plus C1 star C2 star minus C2 star C1 star. Okay, so if we were talking about numbers, this would be 0. If we were talking about a boson field, this would typically be 0 also. But we're not talking about a bosonic field, we're talking about a fermionic field. And so, if we were doing a path integral, we would be representing C1 and C2 by Grassmann variables. And then for Grassmann variables are anti-commuting numbers, although number is used in a very general sense. Or if we're talking about fields, well, the anti-commutator of a fermionic field with itself is 0, at least at equal times and space-like separations. And consequently, this thing is rather a factor of 2 rather than 0. It's 2 C1, C2 in effect, which is why there's a 2 here. Whether there's an extra 2 is another matter. Okay. Now let me show you something that's kind of a trick. There are going to be several tricks today. I guess, is Halloween a trick? Yes, trick or treat. Here we go. So suppose we have a 4-component field that satisfies the Klein-Gordon equation. So I'm sort of doing the inverse of what Schwartz did, but then I'll redo what Schwartz did. So in other words, we have, and I'm going to use, for the moment, Weinberg's metric because the Dirac equation in Weinberg's notation has one less I, and there are going to be a lot of D slashes. So let's do. So for the moment, I'm in Weinberg's notation. So we've got 4 fields that satisfy the Klein-Gordon equation from S. Okay. And now we can define a field chi of x, which is going to be gamma b db minus m times phi of x, phi being a column vector. In other words, this thing would be C, chi C is gamma b CD delta CD phi d. All right, so that's the picture. By the way, you can sit in the front row. You don't have to sit in bleachers. Come over here.
The front, when you come over here. That's
I'll come there. Yeah, that's true. You're in the front row. All right. So now, what I want to say is that chi satisfies the Dirac equation. Right? So we've got a 4-component field that satisfies the Klein-Gordon equation. We define chi as a Dirac-like operator acting on this 4-component vector, and I'm saying that is a solution of Dirac's equation. And the reason is that we have gamma A dA plus M. This is what Dirac's equation is in Weinberg's notation. This then is gamma A dA plus M times gamma B dB minus M times the 4-vector phi. I say 4-vector loosely. It's just a 4-component vector. And now this thing, what is it? Well, you know, high school algebra, A plus B times A minus B is A squared minus B squared. Okay. So this is gamma A, gamma B, dA, dB minus M squared on this 4-component vector. And now we can rewrite this thing. We can rewrite it as 1/2. In other words, I'm going to write gamma A, gamma B as 1/2 the commutator of gamma A, the anti-commutator of gamma A with gamma B, plus the commutator of gamma A with gamma B. So the deal is that this gives us gamma A, gamma B, and that gives us gamma A, gamma B. Divide by 2, you get gamma A, gamma B. But this one also gives us gamma B, gamma A, and this one gives us minus gamma B and gamma A, so they cancel. And then we have, so it's all of that times dA dB minus M squared phi. Okay. Well, this one here is anti-symmetric in A and B. That's symmetric in A and B, once it has B at least. Okay? If you have something that's anti-symmetric times something that's symmetric, 0. always. Do you want me to show that in any detail, or are we happy? All right. So this term is simply 0. This one, by the definition of the gamma matrices, is 2a to ab. So this is a to ab, dA dB minus m squared phi. But this is 0 by, this is just box minus m squared phi, and that's by assumption, by construction, or by assumption 0. So that means that chi, defined as this sort of anti-Dirac form on the 4-component vector phi, is a solution of the Dirac equation. Now, what use this is, I don't know, but it's amusing to note that. And so to say it again, you take just any old 4 solutions of the Klein-Gordon equation, put them into a 4-component vector, hit them with this, and you got a solution of the Dirac equation. I found that surprising when I first saw it.
So what does that tell us physically?
I'm sorry, what?
What does that tell us physically?
Oh, God. No idea. I mean, it tells us certainly that the Dirac particles are going to have mass m. But what else it tells us, I don't know. It suggests to me that there might be a cute way of associating spin 0 fields and spin 1/2 fields. I don't know what it means. I don't know what it means apart from what I just said. Okay, let's just review what gauge theory is. If you want your, this is it's either a single complex field, or it's a several component complex field, or several component real field. U is a unitary matrix, let us say. This then is a gauge transformation. You can make the action in density invariant if you say that AB of x is U of x, AB of x, U inverse of x minus dA U of x, U inverse of x. So I'm speaking here in the general sense in which psi is a vector and U is a unitary matrix, n by n, in which case this gauge field A is actually a bunch of gauge fields dotted into a matrix. In other words, AB would actually be AB, let us say, I, TI, where the T's are the generators, say, of the gauge group. In other words, you have TI, TJ, I, F, I, J, K, TK, where these are the structure constants. But of course, in the case of electrodynamics, what we have is simply psi prime of x is e to the I alpha psi of x, psi of x, and so a prime b of x is ab of x, that's what this term is, and then minus d by dA of this, so minus I d alpha dA, period. Okay, d alpha dA, because when you then multiply by U inverse, you get rid of the phase factor. So this is the standard gauge transformation of electrodynamics, or of a U1 gauge field. And what these transformations, or equivalently these transformations, give us is that the the gauge transform covariant derivative, where by this I mean dB plus AB prime of x, u of x, psi of x. This then is, in fact, u of x dB plus AB of x psi of x, which is to say u of x dB psi of x. Okay, so the idea is that this covariant derivative transforms just according to u. This is the idea behind abelian and non-abelian gauge fields. But gauge theory. By the way, at some point, we're going to take a quick break so you guys can all get a piece of pizza. Somebody might want to be on Pizza Watch to make sure that you're going to be on Pizza Watch, so you're going to make sure that we don't wait too long. All right, so then what happens is that what we have here then is, if we switch now to Schwarz's notation, we have d mu psi is d mu plus I.e. a mu. We're talking now just about, we've gone down to the U1 case, and I'm going to be using Schwarz's notation. And that means that the ordinary Dirac equation, which is I d slash minus m, see, this is the Schwarz Dirac equation, whereas the Weinberg one doesn't have an I there. That's because Weinberg's gammas have an I, because he uses the opposite method. This goes into I d slash minus E a slash minus m psi equals 0. And what does that mean? Well, this thing, of course, is the same thing as 0 is I gamma mu d mu minus m psi. That's, of course, what the slash notation means. And this then goes over into I gamma mu d mu minus E a mu minus m psi equals 0. Okay, so this is the Dirac equation, Schwarz's metric for U1 electrodynamics. Now we're going to do something that might be a little bit confusing. Maybe I'll start over here. Oh, wait a second. I think I skipped something. Yeah, I skipped something, so let me unskip it at this point. The actual Dirac equation is this. Okay, and if we write it in terms of, let us say, psi, then it is gamma A dA plus m psi equals 0. All right? We can then repeat this trick, but in the opposite direction. In other words, we multiply from the left by gamma B gamma B dB minus m gamma A dA plus m psi. So psi satisfies Dirac's equation, multiplied by this, and what we have then is gamma B gamma A dB dA minus m squared psi is 0. And remember, we can take this thing here, write it as symmetric plus anti-symmetric, and the only thing survives is this. Basically it turns into box. And so this thing here is box minus m squared psi equals 0. So that means that if a Dirac field satisfies the Dirac equation, then it also satisfies the Klein-Gordon equation for the same mass. And any questions? So we should take a pizza break now? Is that what
Everyone wants to, yeah.
There is pizza.
All right, well, he's the pizza watchman, so let's take a break for pizza. Maybe you should turn the...
How do you know how to pause this? Or
How what?
pause it?
Recording for all time. There's no way.
No, I don't
Yes,
know. I think you can just turn it off and then turn it back on.
There will be two pieces of
Yes.
videos.
That's fine,
Okay.
it's part 1 and part
Okay.
2.
That's all right.
It's like